see what happens.
Hi. Make sure it's running. Is it running? Yes, it is. Okay, good to see you. Okay.
Hi.
All right, we're going to start on page 130 today. We're going to finish up what we started yesterday. Okay, so it's kind of a short finish up. We'll watch a quick little film clip, and you'll be quiet for a minute. I will address you.
Thank you.
Okay. And then I will hand you out your homework questions. I think there's 11 of them, if I'm not mistaken. Okay, and then of course it comes right out of your reading again. Miller, you would need to probably read starting on page 126, and that would catch you up with us. Okay, that's what we studied yesterday. Okay. All right. Now then, this right here, some of this we're going to talk about today can get a little bit confusing. Okay. No one expects you to actually understand all of it, especially when we get to the HR diagram, because it is it's basically just an introduction to let you understand how they do measure things. No one expects you to actually understand that chart. I gotta be honest with you, I've looked at it, and I think I kind of get it, but it's out there. That's for people that actually studies this stuff for a living and things. That I'm sure they'd be walking here and just tell you exactly what every dot and detail was. But I don't understand every bit of it myself, so I definitely do not expect you to. Yes?
So, in 5th grade, Miss Thrower, she taught us about this stuff. I think we played a game or something. Like with these stars.
Oh, the star charts?
Oh, yeah.
You're not supposed to be teaching your astronomy in 6th grade anymore. That's why I'm doing it in 6th, because.
But why? Why can't they teach you astronomy in 5th grade?
Because we did it in 6th. That's why. Okay. Measuring distances to stars, okay? Imagine you could travel to the stars at the speed of light. To travel from Earth to the sun would take about 8 minutes. Okay? That's not very much time for such a long trip. The next nearest star, okay, is much further away, and it would take you about, going the speed of light, about 4.2 years. So that kind of shows you how far the next star to our sun is. Okay? Okay? 4.2 years traveling at the speed of light. Okay, it takes about 8 minutes to get to our sun traveling at the speed of light. So you kind of got an idea about how far this thing is out there. Yet we see it nice and bright. Isn't that amazing? Yes, Spirit. Spirit. Do what?
But if it was any closer, wouldn't it cause the Earth to heat up a bit more?
Possibly. I don't know. That's a long ways out. I mean, yeah, if it was like 2 blocks away from our sun, it would be, that would be pretty bad. But that's why it's not. God had a plan, man. He had it all figured out. He did exactly what he was doing. Okay? All right, the light year. Distances on Earth's surfaces are often measured in kilometers, okay? However, distance to the stars are so large that kilometers are not a very practical unit of measure, okay? So they use the light year to measure distance between the stars, okay? In space, light travels at a speed of about 300,000 kilometers per second. So a light year is the distance that light travels in 1 year, or around 9.5 million kilometers.
Million?
Million.
What's that?
Okay? That's a long ways.
It's
Okay.
infinity.
Okay? So that's a long ways out. But that kind of tells you how far it is. Now, something you do understand is a light year is not a measurement of time. When we think about a year, we think about time, okay? A light year is a measurement of distance, not time.
It's how much light travels in a year.
It's how far light travels in a year. So it's a measurement of distance, not time, okay? Okay? To help you understand that, consider an everyday example, and this is a really bad example. If you bicycle at 10 kilometers per hour, it would take you 1 hour to go to the mall if it was 10 kilometers away.
That
Okay?
makes no sense.
So you could say that the mall would be 1 bicycle hour away. Told you it was bad. Okay?
That's terrible.
That's pretty bad.
That's actually kind of sad.
Okay? All right, a parallax. Standing on Earth, looking up at the sky, it may seem that there's no way to tell how far away the stars are. However, astronomers have found ways to measure those distances, and they use a parallax to measure distance of nearby stars. Okay? That was what we did with our thumbs yesterday. When you held your thumb up and you covered something, and then you shut the other eye, yeah, it appears different. Okay? That's what a parallax is. Okay? A parallax is the apparent change in position of an object when you look at it from a different place. For example, imagine you and a friend had gone to a movie, and a woman with a large hat comes and sits down right in front of you. That's pretty typical. That's pretty much every time I go to the movie. I can be the only guy in the theater
Why do they wear
with
hats?
2 other 100 seats, and some great big guy will come and sit down right in front of me.
Exactly.
All right, now, a woman with a large hat sits down in front of you, okay? Because you and your friend are sitting in different places, the woman's hat blocks different parts of the screen, okay? If you're sitting on her left, the woman's hat appears to be in front of the large dinosaur in the picture. If she's on the right, it appears to be blocking out the bird, okay? But the woman, have the woman in her hat moved? No, but because you changed your positions, she appears to have moved. So this apparent movement, when you look from 2 different directions, is the parallax, and that's what they do. They pick up these stars from 2 different angles, basically. Okay, that's what they do. Yes, Caleb.
Yeah, so based on how much it moves, using the parallax, they can, with like equations, figure out how far away it is. Because if it was, the more closer it is, the more it moves, right?
And we're actually going to talk about that. Yeah, you're
But
exactly
if
right.
it's farther away, it only barely
Yep.
moves.
Yep, and in fact, I think that's the next thing we're going to talk about. So, very good, but you are correct. Okay? Now, they are able to measure the parallax of nearby stars to determine their distance, as shown up here in Figure 9, okay, at the top of the page on 131. They look at nearby stars when Earth is on one side of the sun, and then they look at the same star again 6 months later when the Earth is on the opposite side of the sun, okay? And then they measure how much the nearby star appears to move against the background of the stars that are much farther away, okay? They can then use this measurement to calculate the distance to the nearby star. The less the nearby star appears to move, the further away it is. And that's kind of what Caleb was talking about. If we went over to, let's say we had a back-to-back-to-back soccer field, okay? You had 300 yards out through there, or better. And Caleb was standing right in front of me, about 10 yards, okay? But Margaret was all the way on the other end, okay? And Margaret's gonna look about this big to me, okay? She's that far away. She's looking about that big. And I had them both move 10 feet in the same direction. Well, Caleb is going to end up way over there, okay? Margaret is going to look like she barely has moved, but she's moved the exact same distance, okay? But because she is so far away, it doesn't appear that she has moved this far. And that's what they do. That's how they can determine these stars, okay? They have figured this out and they can run the calculations, and they can figure out about how far away these stars are by the movement like that. It's really pretty cool. It's like up here over most people's head, but if you understand it, it's pretty cool. Well, I think it's cool, and I don't fully understand it, so I don't guess you have to fully understand it. I think it's pretty amazing that they can do that. Okay? Now, on page 132, the Hertzsprung-Russell diagram. This is a mouthful. I'm going to tell you right now before we even get into it. This goes on, and again, this is just an introductory. No one expects you to understand how to read this chart or anything like that. So don't be sitting out there starting to panic and freak and think, oh my gosh, am I going to have to draw this on the test? No. I can put your mind at ease right now. You do not. Okay? Okay. Now this right here, though, is pretty amazing. About 100 years ago, two scientists working independently, one of them was in Denmark, and the other one was in America, and they don't realize the other one is working on this, and they have come up with the exact same theory. Okay, they're studying the same thing, and they come up with the exact same theory. That's pretty amazing. Okay, so Hertzsprung in Denmark and Russell in the United States makes graphs to find out if the temperature and the absolute brightness, remember we talked about absolute brightness and all that yesterday, of the stars are related. They plotted the surface temperatures of stars on the x-axis and their absolute brightness on the y-axis. Now, some of you are probably starting to get into plotting stuff. Have you done that yet? If you're in pre-algebra?
Pre-algebra.
You will. And it's actually quite fun once you know how to do it. It's kind of fun to plot stuff like that on the y and the x-axis. If you've never done it, you're not going to understand what we're talking about. And this is flying because I realize this is kind of advanced. That's why this is not,
Isn't it
don't worry
like
about
the
this.
charts with like the down is X and then the cross is
It-
It's like
yeah,
in
it
an
depends.
it's like in an army math.
Okay.
They're able to
Yes,
plot
yes, it is. Yes, it is.
Of course, spears and atoms.
Okay. All right. Now, and the points formed a pattern once they put it on their chart. Okay. And the graph that they made is still used today, and it is called the Hertzsprung-Russell diagram, or the HR diagram. They actually lowered it down a little bit instead of have to say that mouthful every time they refer to it. Okay. So they use the HR diagram to classify stars and to understand how stars change over time. Okay? Most of the stars in the HR diagram forms a diagonal area called the main sequence. Okay? Here's the good part. More than 90% of all the stars, including our sun, falls in that main sequence. Over 90% of all the stars. That's a bunch of stars if you think about that. Okay? That's the surface temperature increases as absolute brightness increases. Thus, because of that, the bluest stars, which are the bluest stars?
the hottest.
The hottest, yeah, the hottest. The ones with the
It's
highest
kind of like your
temperature.
oven. When you turn it on, the fire sometimes turns blue because it's so hot.
Because it's hot, yeah, there you go. That's it. Okay?
Or
Anyway, so the bluest stars are located to the left. The cooler reddish stars are located at the right of the diagram. The brightest stars are located near the top of the HR diagram. The dimmest are located at the bottom. The giants and supergiants are very bright, so obviously they can be kind of found top center there. Okay? The white dwarfs are hot but not very bright, so they appear more at the bottom left of the diagram. Okay? Again, you would have to really study this thing and have more. You would need more information to actually understand this than what we're getting in a paragraph. But if you ever get into astronomy and you really enjoy it, this is some pretty interesting stuff. And I recommend when you get into college and you do have to take electives and all, take an astronomy course. It's just your general astronomy. It's pretty interesting stuff, it really is. So, anyway, yes, Kayla?
This diagram is pretty cool and I understand it.
There you go. We got an astrophysicist in the making, okay? Thank you for watching and talk to you later.